Alright folks, today we're going to talk about thermodynamics and heat, which is another form of energy. So if you take a look at the thermodynamic notes, you guys should have the option to print these. I recommend taking the notes by hand, and then these of course can be used on future homework assignments and also test and quizzes. So here it is from the beginning. What is temperature? We're going to try to explain the difference between temperature and heat because they're often in just general conversation, or you might hear people say, oh, this is hot, or go get the heater, or something's going to warm things up, or whatever. We've got to really distinguish the difference between temperature and heat because they're definitely not the same thing. Temperature by itself is the average kinetic energy of a substance. What are some of the limits to this? Well, maximum temperatures, I guess we can go as high as you want, but as far as absolute zero, the lowest we can possibly go, this is where they would say that all kinetic energy is gone from matter. So if you get a piece of matter, like a glass of water, and the molecules are wiggling around, if you cool it down more, the molecules will turn into a solid and they wiggle less. And then if you could cool that ice down to a point where it couldn't cool anymore and the perfectly aligned and there would be no entropy or chaos in the molecules, they would completely stop moving, that would be absolute zero. All particles have kinetic energy that are above absolute zero, which makes sense. If they have a temperature, that means something inside of them has to be moving. So even things that are solid, an ice cube or a chunk of wood or a chunk of steel, even though they look as if nothing's moving or flowing, the particles inside are kind of wiggling back and forth just a little bit. So they do have some sort of energy. And how do we measure temperature? Well, there's different devices for measuring temperature, but the scales that we use in the United States, of course, we're most commonly referred to as the Fahrenheit scale, and it's a little bit, doesn't work as well in science as, say, Celsius or Kelvin, just because of where certain things happen. For example, water boils at 212 and freezes at 32 degrees Fahrenheit, which seem like kind of odd numbers, just picked at random per se, where when you look at the Celsius scale, it makes a little bit more sense. Water boils at 100 and freezes at 0. So, believe it or not, a lot of the basis of the Celsius system, the metric system, the cubic centimeter, when we talk about a calorie and a gram and all of that, a lot of it was based upon density, volume, mass, and characteristics of water itself, which kind of makes sense because it's very common. And then the Kelvin scale. The Kelvin scale is similar to the Celsius scale in the fact that it's the size of a Celsius or a Kelvin. Like if you increase by 1 degree or decrease by 1 degree, you're increasing by the same amount, where with the Fahrenheit scale, 1 degree Fahrenheit and 1 degree Celsius, if you increase by those two, it's not the same. And we'll talk about those conversions here in just a minute. But water boils at 373 degrees and freezes at 273 degrees. You will see that this scale is offset by 273 degrees. The whole idea of the Kelvin scale is that it bases things from what is absolute zero. So if we want to start counting from what is truly absolute zero, you'd use the Kelvin scale. So if you wanted to go to absolute zero, which we showed up above, as being negative 273.15 degrees Celsius, well, absolute zero in Kelvins is basically zero. 0 Kelvins is absolute zero. So how do we convert temperatures from one scale to another? I have 3 equations here, and these are kind of base equations that we can use to go from Fahrenheit to Celsius and Celsius to Kelvin, or Kelvin to Celsius and Celsius back to Fahrenheit. So we'll do a little bit of rearranging. I got a couple of example problems that we'll go through, and just know that, so remember that I told you that a Fahrenheit and a Celsius are not the same size. So when we look at this, to get a Fahrenheit, you need to have Celsius multiplied by 1.8, and then they're also offset by 32 degrees. So when you go from Celsius to Fahrenheit, you got to first multiply by 1.8, which is the same as 9/5, and then also add 32. When you go from from Fahrenheit to Celsius, you have to take your Fahrenheit minus 32, so there's the offset of 32, but then you got to divide by 1.8 to get to Celsius. Kelvin and Celsius conversions are easy because again, they're the size of, like looking at a meter stick, where we can measure in centimeters anywhere on the scale. If I want to measure 10 centimeters, I can start at 0 and go to 10, or I can start at 80 and go to 90. I'm still measuring 10 centimeters across because a centimeter is a centimeter. Think of that like Celsius and Kelvin. But if you go to inches, if I measure 4 inches or 5 inches on the inches side, and then I go and measure 4 or 5 centimeters, it isn't going to be the same size, obviously, because the size of the unit is different. So for example number 1, they're asking us to convert 45 degrees Fahrenheit to Celsius and then also to Kelvin. So the first thing we're going to do is we're going to go from Fahrenheit to Celsius. So the equation that we have says Celsius is equal to Fahrenheit minus 32 degrees divided by 1.8. So if we plug in the values that we got, our Fahrenheit is 45 degrees. We got a minus 32 for the offset, and then we need to divide by 1.8. And if we do that, we're going to get 7.22 degrees Celsius. So there's the first step. Then if we're going to go to Kelvin, there's basically one more step. So a Kelvin is the Celsius plus 273. So a Kelvin, we're going to do Celsius plus 273. So then I'm going to take my 7.22 and I'm going to add 273. And that's going to give me my grand value of 280.22 Kelvin. Okay? And of course, if you're going to go in the opposite direction, which we'll show in the next example, you could just flip these equations around and solve for the proper unknowns. So for number 2, they give us 452 Kelvin, and they ask us to go to Celsius and then to Fahrenheit. So for this one, if we want Celsius and we have Kelvin, the equation now is just a little bit different. Instead of adding 273, we're going to subtract 273. So I'll plug in what we got for Kelvin. We got 452. I'm going to minus 273. And this is going to give me 179 degrees Celsius. And then we're going to go from Celsius to Fahrenheit. So the Fahrenheit equation from Celsius, we're going to do 1.8 multiplied by the Celsius. And then we're going to add 32 to this. So all we did is we took this equation that was here. These two equations are kind of inverses of each other, I guess. Plug in what we got. I got 1.8 multiplied by 179, and then I'm going to add 32. Make sure you multiply before you add, and if you do that, you should get 354.2 degrees Fahrenheit. There it is. Alright, so now that we've addressed what temperature is and how to convert between some of the scales, we're going to talk about what happens when things change temperature. So these could be solids, liquids, or gases, or plasmas. Any of those forms of matter could all exchange energy from each other depending on how they make contact. And this is a list of different forms of energy transfer in the form of heat. So again, heat and temperature are really not the same thing. If there's a change in temperature, then heat must have been gained or lost. And heat is, the definition for heat really is the transfer of energy between two substances that are different temperatures. So if you put a hot thing next to a cold thing or a cold thing next to a hot thing, the hotter object's going to go and flow into the one of lower temperature or lower energy. So it always goes from high to low or hot to cold. So ways this can happen is through conduction, and conduction is when two solid objects touch each other. So if you had two pieces of metal, one was scalding hot, one was ice cold, and you touch the two pieces of metal together, those solid surfaces make contact, and the molecules will bounce off of each other, and the hot one will warm the cold one up. Convection is movement of matter and energy due to differences in temperature. This can pretty much only happen when things can flow. So they talk about the movement of molecules. So inside of a room, if a heater turns on, the hot air wants to go up and the colder air wants to go down. It kind of causes convection currents. This can happen again in water, fluids, liquids. The ocean would be a good example. When water warms, it rises to the surface, and cools, it sinks. That can happen. Again, you got a hot cup of coffee and you pour some cold creamer in it or something, and the creamer sinks to the bottom, but you will notice that it does it almost mixes itself up, especially if you wait long enough. It normally will kind of reach entropy and kind of blend together. Radiation, this is probably the most critical form of energy transfer that we have on Earth, because this is how we get all of our energy from the sun. So radiation can transform energy in the form of electromagnetic waves, and from the sun, everything we get from there, will hit the atmosphere, gets absorbed, and you're taking heat from an outside source, or energy from an outside source, and bringing it into the Earth where we're at, which is good because that grows plants, and things we eat plants, or we just eat plants, or vice versa. But we got to have it because that's our main form of energy. Conductors. An insulator, so a conductor is something that does conduct heat well. I mean, most things will conduct heat to some extent, but some are better at it than others. Better than others at not conducting heat. So if you have a pair of wool socks on in the winter, wool's a good insulator. It isn't such a good conductor. It's a better insulator, so it'll hold heat in. It doesn't want to transfer the heat through it as well. Things that are good conductors, say such as metal, well, if you go outside and touch a cold metal railing with your bare hand, you'll probably feel as if it's even colder than it presents itself to be, because the rate of heat transfer is more dynamic than maybe if you touch something that was insulated. Not to say that they aren't potentially at the same temperature, it just appears as if they feel colder, which is kind of interesting because our sensory for temperature with touch is often exaggerated by how quickly the energy goes from one form to another. Specific heat is the ratio or the rate or the factor that determines how much energy it takes for a certain substance to either gain or lose energy in the form of heat. So some things you can heat up and cool down very, very easily, and those would be said to have things that have a very low specific heat. And then there's things that require a lot of energy to change their temperature and exchange heat, and those would be said to have a high specific heat capacity. So here's an example, a table, and then we'll talk about the equation here a little bit also. Here's some basic units or materials you probably use, and of course water being the first one on there. This is given in two different units. One is a joule per gram degree Celsius, and of course a joule is a measurement of work or energy. So we talk about a force multiplied by a distance. How many joules, how much work do you put into this? Same idea. Remember, energy is energy is energy. It goes mechanical forms, chemical forms, electrical forms. It can be transferred all over the place. And then this other, which is potentially in our everyday world, the calorie per gram degree Celsius. Water has a specific heat of 1 calorie per gram degree Celsius. And what that means is if you had 1 gram or 1 milliliter or 1 cubic centimeter of water, which is all the same thing, if you try to increase its temperature by 1 degree, it would take 1 calorie. Now, these are not necessarily food calories, because a food calorie is really 1,000 of these calories. So we'll do some of these calculations like, if you melt an ice cube that is 20 grams, how many calories does it take? And you might look at it like, oh, it's hundreds of calories. How do I not lose weight by just eating ice cubes? Well, you'd have to divide that by 1,000 to see how many, food calories in our terms of calories that you would really be burning. So we'll talk about that a little later. But we have a few different items here, tells us specific heats, and of course anytime you have a standard table of something, something to multiply by with the ratio, of course we're going to have an equation to go with it. So this is sometimes called latent heat equations. The left-hand side is talking about the amount of heat gained or lost. It's symbolized by Q, but say we're going to measure this in terms of calories, so we'll focus using the calorie instead of the joule. M stands for the mass of the substance. The C here stands for specific heat, which would be coming from this table. And then delta T, of course delta meaning a change, and T being the temperature. And you can almost tell by looking at the units here, a calorie divided by a gram degree Celsius. If you multiply by mass, gram, and you multiply by your change in temperature in terms of Celsius, you're going to be left with just calories, and that's what we want on this side, is calories. So that's what we're going to do. So we're going to do a couple of example problems here, talk about how energy is transferred in the form of heat. So example 3 says, how much heat or how many calories will it take to increase the temperature of 50 grams of water from 30 degrees Celsius to 95 degrees Celsius. So if we look at our equation, we're going to want to write down some of the variables that they give us. They tell us the mass of the water, and the specific heat, C, which is sometimes just written as SH or C, of water is 1 calorie per gram degrees Celsius. We said the mass of this was 50 grams. And then delta T is the change in temperature. Well, they tell us it starts at 30 degrees Celsius and it ends at 95 degrees Celsius, so it increased in temperature. And if we subtract those out, you're going to get 65 degrees Celsius. And this again is the change. If I want to put it as a plus, I can. So we'll plug it all into the equation that we got. We know that the change of heat Q is equal to the mass. So we got 50 grams for the mass multiplied by the specific heat of water, which is 1 calorie per gram degree Celsius. And then we're going to multiply that by the change in temperature, which is 65 degrees. And if I plug all of that in, I get 3,250 calories. Now again, alright, here's example 4. They're asking how much heat is transferred if 100 grams of lead cools from 112 degrees Celsius to 40 degrees Celsius. So the mass that we got, so they give us a mass of 100 grams, they give us the specific heat, equal to 0.031 calories per gram degree Celsius. And then we got the change in temperature for this is going to be a decrease because it goes from 112 down to 40, so this changes by negative 72 degrees Celsius. So, plug it into our equation. We're going to do mass, 100 grams, multiplied by the specific heat of lead, so 0.031 calories per gram. And then we're going to multiply that by this negative 72 degrees Celsius. So the negative side is going to come into play because when we get a value here, it's going to be heat lost. So it does make sense to say that this is a negative. So I get negative 223.2 calories is how much energy was given off. So even though the change in temperature of the lead was more than the water, you can see the actual heat lost or gained, depending on what side of the system you're on, was quite a bit less. So looking at the next page, what you guys will see here is a temperature and heat table. So this is showing how much heat is gained by going through some phase changes here. So they're going to use water, so this is a pretty classic example. The water starts at a certain temperature over here at, say, negative 40 degrees, and ice can be, a different temperature. I think sometimes that's a misconception where people think, well, ice is ice, it's 0 degrees, right? No, there's ice that's colder than others. You could have ice at negative 20 degrees Celsius, negative 40 degrees Celsius, negative 80, and so on. So let's say, for example, we started at negative 40 degrees. You have to heat the ice up to even get to 0. Once you get to 0, there's something called the heat of fusion, which is telling you how many calories per gram it takes to melt the ice, and it's approximately 80 calories to melt 1 gram of ice. So if you had a gram of ice and it was at 0 degrees, just to melt it would take 80 calories. So you'll see that the line flattens out here because all you're doing is adding heat, but there's no change in temperature. So all the way up until all the ice melts, and once the ice melts, then the water will heat up. So using ice cubes to keep a glass of water cool, the temperature in theory, if you could continually mix or stir, the temperature of the water at liquid, if it was put in at around 0 and the ice cubes were below 0, you should be able to maintain that temperature all the way up until that last ice cube melts. And then once that last ice cube melts and all of the heat has gone into, going through the phase change of the ice, then finally the water would start to warm up. So, warm up the water, we got to go from 180 calories per gram to melt the ice, 540 calories per gram to turn it into steam. So if you're trying to boil water, this is part of the reason it could potentially take a while and takes kind of a lot of energy to do so. And then, when you get beyond here, you can heat steam up, of course, to different temperatures too. So the steam itself has the same, steam and ice have the same specific heat. This is a half a calorie per gram, and so is the steam. So what we're going to do is we're going to take a look at example number 5. Alright, so now we're going to take a look at example number 5. And in example number 5, we're going to go through phase changes and we're going to go through heating up of material. So the example says if you have 200 grams of ice and the ice is starting out at a temperature of negative 20 degrees Celsius, if we're going to heat it, melt it, heat up the water, and then vaporize the water to a temperature of 120 degrees Celsius, how much heat would need to be added? Well, there's a lot of steps here that need to fall into place. The first thing that has to happen is you need to warm the ice, because the ice itself starts out at negative 20 degrees Celsius. We need to warm it right up to 0 degrees Celsius before we can melt it. So in order to figure out the heat needed, the heat for this, you need the mass of the ice, which is 200 grams. We need to multiply it by the specific heat of the ice, which is 0.5 calories per gram degree Celsius. And we need to go from negative 20 to 20 degrees Celsius. So that's a positive 20 degrees Celsius is the change. So if we multiply all of that out, that's going to tell us how many calories it takes to warm the ice. So if I do 200 times a half, gives me 100 times another 20, gives me 2,000 calories. And that's just to warm the ice. Now that we've warmed the ice, we need to melt the ice. Now, when we try to figure out how much energy it takes to melt or vaporize something to go through a phase change, there's no temperature change during a phase change. In theory, there should not be, if you have ice at 0 degrees and you have water at 0 degrees, there can still be a whole bunch of energy put into that or taken out of that in order to just melt or freeze, vice versa. The heat of fusion, they would say, is equal to 80 calories, approximately 80 calories per gram of the ice. So these calculations are a little easier. We just take the mass of the water or the ice and you multiply it by the heat of fusion, which is 80 calories per gram degrees Celsius. So for every single gram of ice or water to melt or freeze, solidify, you got to put in 80 calories. So in this situation, since we're melting, we got to put in 16,000 calories. So that's a plus. It's got to go into the ice cube. All right. Well, now we have 200 grams of water, and we need to warm the water up. So now we're going to warm the H2O that's left over. So to figure out the heat that goes into that, we still got 200 grams of water. Got to multiply that by the specific heat of water, which is 1 calorie per gram degrees Celsius. And then we're going to increase that from 0 all the way up to 100 degrees. So we got to add 100 degrees Celsius to this. Then if we multiply this whole thing out, this is going to give me 200 times 1 times another 100 is going to give me 20,000 calories. So now I have water at 100 degrees and it's ready to boil. But if we're actually going to boil or vaporize the water, we need to add more heat. And it's a lot of heat. Every gram of water requires approximately 540 calories. 540 calories per 1 gram just to change it from water to steam. So that's a huge input of energy. So if we multiply that all out, I get 108,000 calories. So way more energy input just into that one stage than all of the other stages combined so far. And then the last thing we're going to do is we're going to heat the steam, because they told us that we want to go all the way to 120 degrees. So I'm going to take my 200 grams of steam that I got, multiply it by the specific heat of steam, which is the same as ice. It's 0.5 calories per gram degrees Celsius. And then I'm going to multiply that by the change in temperature that we have, which is the 20 degrees. If I multiply all that out, I get another additional 2,000 calories that has to go into it. So if I want the grand total for the total amount of energy that it takes to go from a negative 20 degree Celsius ice cube to a 120 degree chunk of steam with only 200 grams, it's going to take 148,000 calories, which is, again, seems like a fair amount, but remember, these are scientific calories, not so much food calories. All right. Now we'll take a look at all the laws of thermodynamics. It's often that they only talk about the first and the second law, and the 0th and the third law kind of get swept aside, but we're going to briefly look at each of them. So this is a general summary of the laws. The 0th law of thermodynamics is basically talking about how any objects that are left in the same area or in contact with each other that are exchanging heat are basically going to reach a temperature equilibrium at some point. And it's simply stated that if the temperature of object A is equal to the temperature of object B, and object B is equal to the temperature of object C, then of course C must equal A, which kind of makes sense. If A equals B and B equals C, then C must equal A. And it might seem kind of redundant to kind of state that, but basically what they're saying is that anytime you have objects or materials of different temperatures blended together, they're sooner or later going to reach a consistent temperature, whatever it happens to be. You could have a warm glass of water, you could put in a ice cold ice cube, and you could pour in scalding hot milk, and stir them up, and if you let them sit over time, of course the ice will melt and get warmer, and the warm water will take energy in from the hot steam, and they'll reach a common ground. The first law of thermodynamics, this one also follows the law, just the law of energy, the conservation of energy. It basically says that the total energy used in a process is conserved, so the total amount of heat within a closed system is not ever created or destroyed. It's really going from one place to another. It's going from one form to another. And if you look at things in a small form, it's sometimes hard to imagine, but you got to look at it even in the bigger picture. Any energy that was put in had to have gotten taken out or transformed from one thing to another, from the hot water to the ice cube and vice versa. Like the total amount of energy is the same. It's out. Second law of thermodynamics, when energy is transformed, heat always moves from a higher energy to a energy of lower energy, or hot to cold, high temp to low temp, meaning the flow from hot to cold will create more entropy or disorder. So this is basically saying if you have molecules that are very cold, the colder they are, remember, the less they move, the less kinetic energy, the less motion. They would sometimes say that is more organized, more structured. Think of like a crystalline structure, things that solidify. They organize themselves, and if the molecules could somehow be perfectly organized and had zero movement or energy, they'd be at absolute zero, which they say isn't perfectly true for us here in most all daily life. But the more energy that's put in, or the more chaotic things want to become. And then the third law of thermodynamics is the lower the temperature of a substance, the less entropy the system will have. Kind of similar to what we're saying here, more temperature, you have more entropy. This is just saying that if you could get to absolute zero, then the entropy would be zero. Create something, nothing's ever going to go back to zero. Like, things are not going to organize themselves. If you have an ice cube and you melt it, there's no way that it's going to refreeze itself. Or if you take, a glass of some sort and you shatter it on the ground, it's never going to put itself back together without some other work being done. So that's basically what this is saying, is things never are going to go backwards. The entropy part of it never goes backwards within a system unless some other system can be part of it to put it back into place. So, alright, that's about it for the notes. Take a look at the announcements, and if you guys want, you can again use these on test and quizzes and homework. If you have any questions this week, please feel free to get a hold of me, and I'll do my best to contact you back. Email is the best contact, so thanks a lot, and you guys have a good week.